In this video, I want to talk a little bit about rings, some definitions, and some perhaps weird results. Rings are centrally related to algebra, being one of the ways we define polynomials in modern mathematics. They give us the basis for how we think about addition and multiplication in many different relations and scenarios. Now let's get to a definition of a ring. As we see here, a ring is a triple with a set and two symbols, which we call addition and multiplication. And such a set is a ring if the following conditions hold. Addition and multiplication must be binary operations on our underlined set, which means that they must take a pair of elements in our ring and put them back into our ring. Now we further need that our underlined set considered with the additive operation is an abelian group, which simply means intuitively that the set works nice, how we intuitively understand addition to work, and that it has an additive inverse, it has an additive identity, and that it's abelian just means that it doesn't matter which order you take the addition in. Now we demand that it doesn't matter which order you multiply together the elements in your ring with regards to parentheses, which means it doesn't matter where you put the parentheses in a product, it will be the same no matter what. And then we furthermore demand that products distribute over sum like you normally do in regular algebra or arithmetic, that it distributes over the sum, and that it doesn't matter on which side you distribute, whether in front of the parentheses or after the parentheses. And that is our definition for a ring. You can prove from these axioms of a ring that something times the additive identity must be the additive identity, which we can use to answer the following question. What if the binary operations are the same? Well, since every element is equal to itself adding its additive identity, then we can also say, since plus and multiplication are the same in this case, that A is equal to itself multiplied by the additive identity. But we just established that was 0. So A would be equal to 0, which means that every element would be the additive identity, which means that our ring would just consist of the additive identity. Some examples of rings are the integers, the real numbers, and the complex numbers. Our definition of ring cannot contain all of the algebra that we know. So we need to make some more definitions about some more structures that we often work with. For example, commutative rings. Commutative rings are simply rings where the product relation is commutative, which means that it doesn't matter which order you take the product in. We also need to define a division ring, which is a ring with a multiplicative identity, which we'll call 1, which is different from the additive identity. And we also demand that every element that's not the additive identity has a multiplicative inverse. An example of something that's not a division ring would be the integers, because 2 does not have its multiplicative inverse within the integers, which would be a half, which is not an integer, but something that is a division ring would be something like the real numbers. Now we get to define a field, which is one of the most important algebraic structures, which is just a commutative division ring. Now we can define polynomials more generally and more rigorously. So we define a polynomial ring to be the set of all functions from the natural numbers into our commutative ring of choice, such that the amount of points in the codomain of the function is finite. We then call a polynomial anything which exists in a polynomial ring. The intuition behind this is that we can put an order on the coefficients such that we can represent our polynomials as a sequence of elements in our ring ordered by the natural numbers. So we can represent a polynomial as a sequence containing the elements in our ring, which are to be interpreted as we would normally interpret polynomials. Here is an example where our cumulative ring has some of the elements of the integers, namely it has the elements 1, minus 2, and 3. And on the right hand side, you can see what that would intuitively normally be interpreted as. The equality here is not meant to be taken literally. But when our polynomials then equal, well, we can say two polynomials are equal if each of the elements are equal, and we can take the sum and product of polynomials by likewise ascribing them a pointwise meaning. For example, sum, you can simply sum the individual elements together point by point or by order. That was it.